Hello everyone! In this video we will learn how to simulate time-varying loads in COMSOL multiphysics. So what are time-varying loads? Well, in this particular example that I'm going to explain today, we are going to assume that a plate deformation is caused by a central force. This is the central force. And we are going to assume that the plate is constrained on the edges. This is basically the COMSOL model, the COMSOL 3D rendering of stresses and strains. And we are going to learn how to simulate the response of such a system, that is deformation and stresses, for the force that's an arbitrary function of time. So if this is basically the time, this is the force magnitude in newtons, we will learn how to set up a COMSOL study such that you can compute the system response for any kind of shape of a function that you can define in MATLAB or in some other programming language. In order to demonstrate the basic principle of defining time-varying loads, I'm going to use a structural mechanics module. However, the same principle can be applied to other modules such as heat transfer, such as electromagnetics, such as optics, and other modules, MEMS for example, and other modules in COMSOL multiphysics simulation environment. For example, the time-varying load can be a heater applied at this point or randomly distributed over the surface, or can be another type of a load used in, for example, in electromagnetic simulation or joule heating, or for example it can be in fluid dynamics, some kind of pressure change, an actuator or similar device. To give you a flavor of what I'm going to explain today, I'm going to show you first the final result. So basically what you can see over here is the deformation of a plate that's constrained on the edges, and here is basically the function that I apply. So this is basically my time-varying force that's being applied at the center point of this surface. And here is the response at the center point and on the point arbitrarily located. So you can see basically that your input that your output reproduces the applied input. Okay, so let's start from the beginning. We click on Model Wizard, we click on 3D, we choose Solid Mechanics module. However, you can also find it on Structural Mechanics, Solid Mechanics. You click on Add. And let us choose the study now. Click on Study. Since we are looking into time domain, deformations, we're going to select time dependent. And we click on Done. Okay, so this is our main window. The first step is to define the geometry. We do right click on geometry, we click on cylinder. And here we're going to choose a radius of 1 meter and the height of the cylinder is going to be, let's say, 5 centimeters. We click on build select. Here's our plate. Okay, the next step is to choose the material. We do the right click, add material from library. We expand, we click on build-in materials, and let's just select some aluminum alloy, an arbitrary aluminum alloy. Here are the basic properties: density, Young's modulus, and Poisson's ratio. These are 3 parameters that we need in our study. Okay, so the next step is basically to define the boundary conditions. We click on Solid Mechanics, right click, fix constraint, And we're going to select these outer edges to be our boundary conditions. Okay, so these are our boundary conditions. We are assuming that the plate is constrained on the edges. And you click on Build All. Okay, now the next step is to define several points that we are going to consider in our simulations, or whose deformation we are going to track. So to define these points, we click on Geometry, right click, and we click on basically More Primitives, and we click on Point. Okay, so we're going to create a point located 0, 0, 0, located at basically center location, and we're going to define 4 additional points. We can click on Duplicate. We're going to assume that these points are displaced, for example, 4 in the x direction, then we duplicate this point again, and we have another point here, and we repeat this. We choose these 2 points, we click on Duplicate, and here we'll put 0, and here 0.4, and here 0, and minus 0.4. We click on Build Select, we click on Build Select. Okay, so these are our points. This point will be used to define the load, and these 4 points will be used to define spring mass damper constraints, such that we can attenuate, we can dampen the oscillations of the plate. The next step is to define time parameters that we are going to consider in our simulations. So if you click on parameters, if you click here, you can define 2 parameters. Now I'm just copying and pasting from my previous simulations these parameters to save time. So the first parameter is going to be our discretization step. In this case, it could be 10 on minus 4. So every 10 on minus 4 seconds, we are going to look into displacement of our system, or we are going to obtain a sample of displacement. And total discretization time is going to be 0.05 seconds. Why these values are so small? Well, because the system itself, its time constant, is very short. We are talking here about the time constant of maybe a millisecond or several milliseconds, since this is a very fast system. Okay, now since we have time constant, we can proceed with definition of our force, of our load. So first we're going to assume that we have 4 mass spring damper systems attached to these 4 points. So we click on Solid Mechanics, we click on Points, and we click on Spring Foundation. Okay, so first we're going to select the points. And then we're going to choose the type of the spring we're going to use. We can have several options. Force is a function of extension. We're going to choose this option, and we're going to assume that basically our stiffness constant is placed over here. We're going to assume 100 Newton meters. Okay, and then we are going to assume a type of a damping. Viscous damping, we are going to, for example, assume isotropic damping, and we are going to select a relatively large value. Since we don't care in this simulation, this is not a realistic simulation that can be used to describe any particular object. This simulation is only used to describe the basic principle of defining a time-varying load. Okay, now we have our spring foundation. Okay, and the next step is to define our load. So we click on Solid Mechanics, we click on basically we need to search for basically point, right? Point, roller, mass spring, pairs. You have a lot of options here, so we need to find a point. So Before I explain how to define a point, you can also have other possibilities here. You can define a free boundary condition, boundary load, right? Fixed constraint, prescribed displacement, roller. Then connection, you can also play with the connection. You can play with mass spring damper systems. You can choose more constraints. And here is our point, right? And in this case, we're going to choose a point load. Click on point load. Now, in the first step, I'm just going to simulate the system response to constant force, right? I'm assuming just a constant force to get the step response of the system. So here I'm going to assume, let's say that we have 1,000 newtons acting on a system. And I need to choose the point. Here I choose the central point. And we click on build all. Now, the next step is to define our study, to define the parameters of the study. Here, if you click on study and on time step 1 time dependent, we can choose the times for which we are going to simulate our system response. Well, if you go back to our parameters, the first step is to say to COMSOL, I'm going to look at my system at discretization steps, right? At predefined discretization steps. And you need to define the total simulation time. We're going to paste here total simulation time. So this range means that you're basically going to look at the displacement of your system at the time steps zero, then h, then 2h, then 3h, until the total discretization time. In our case, this total discretization time is denoted by total discretization time. This is basically the total discretization time. And h is basically our discretization step. In our simulation, this is nothing less than the vector discretization step. H is the discretization. And this command, range, ensures that you properly define a time vector. For example, if you would write down range 0, 0.01, 0.05, we will look at the deformation of the system at the point 0, 0.01, 0.02, 0.03, 0.04, and 0.05. Okay, now that we have defined the time vector, we can proceed with system simulation. We click on study and we click on compute. Here you can track the progress of your simulation. And what you can see here, you can see the surface von Mises stresses, right? These are the standard graphs generated by COMSOL Multiphysics. If you click here, you can basically see the direction of the point load, how the point load is acting. This is nice to visualize how your system will deform. And let's say if you want to get the displacement, you click on result, you click on 3D point group. Here you can basically choose, for example, surface option, and instead of this parameter solid displacement, you click here. You go into this basically menu, and you basically need to select displacement, and for example we want to look into the total displacement, or we want to look at displacement field Z component, and you click on W. Okay, so this will be your displacement. We are talking here about micrometer displacements that's expected. Now let's look at the time response of our system. If you click on results, you click on 1D point group, and under 1D point group you click on point graph. Point graph is basically a function defined at certain point. We'll click here, we click at the point 7, and we're going to look at the total displacement in to point 7. However, you can replace this by any type of variable, internal COMSOL variable that you can imagine, and you click on plot. Okay, so this is what we get. This is what we get. This is a very well damped system, relatively damped, right? And we see the system response. Okay, so far so good. We are able to simulate the system response for basic constant load. Let us now try to generalize this to time varying loads, to time varying forces. So how to do that? How to do that? That's the main question, the main point of this video. Well, I'm going to use MATLAB. I'm going to use MATLAB here to define a time varying function. So I'm opening the MATLAB script. I'm setting the discretization time, discretization step. I'm choosing the total simulation time, which would be total discretization time. And I'm generating here just a simulation time vector. Okay. Here I'm going to generate sinus x plus x function that looks somehow like this. However, you can play with any type of a function that you want to use. So I'm going to use a function that looks like this. This would be sinus omega x plus some function, let's say kx. This is the function that I'm simulating. This is time, and this will be the force, right? Force in newtons. This is how my function will look like. How to define such a function in MATLAB? Well, it's super easy. Here you defined, let's say, omega is 250 times the simulation time plus 100 times simulation time, and let's execute this. Let's see what do we get. Okay, so what do we get? Let's see. Here is our function. Here is our function, and we can also, of course, scale this function, which is not a bad idea. Since this will be in newtons, we can put here, let's say, 50, or let's say 100, why not? And here is our function. So this will be 500 newtons maximum value of our force. Now, the catch here is to save this function into a folder as a txt file. So with this line of code, I can basically define a data vector, a data matrix, where I'm basically stacking times. So the first column of this matrix, let me just scroll until the end. The first column is time, and the second column is the force. Okay, so at 0, 0, force is 0. At 0.0001, the force is 3.5, etc. Okay, and you write this, you save this matrix as a txt file, right? I'm going to save it as a txt file. I'm going to give it input1.txt, and this will be the name of the matrix. Now, it's very crucial here that you save this file in the same folder that COMSOL is using, right? Where you saved your original file, this particular file, this data file should be saved, right? In this case, my MATLAB knows. I set in MATLAB, I gave to MATLAB the path to my folder. So when I do this, in that folder, time varying load, I will have this file. This is very important. Okay, let's go now to our COMSOL simulation. Now, How to define a time-varying function in COMSOL multiphysics? Well, under the definition sections, we do a right click and we can select functions. And you have several options. You can select, for example, an analytic function if you know the analytic form, which in this case we know, so we can also use an analytic function. However, I like the interpolation. The interpolation gives you more flexibility and more freedom in defining functions. Now, here under the data source, we are going to select file, and then we are going to browse the file, and then we have to locate our source file. So we click on C. In my case, it will be C folder, codes, COMSOL tutorials, time varying load, and this will be our function. Okay, now. Here, it's very good idea to define the units. The first unit will be basically time unit, will be seconds, and the function will give as an output newtons. So the arguments will have the value of time, and the function will have newtons as its value, and we can call the function load. Here you basically call the function, right? You name the function, you do plot. Let's see what we have. Okay, great. This is our function. This is our function that defines an external load. Now, we are almost done, basically. What do we do? Under the solid mechanics, we click on point load, and here, instead of this fixed value, we are going to put load of time. Okay, this will be the load of time. Now, our COMSOL knows that basically this function is defining a time. So when in your simulation, whenever COMSOL is getting its results for, let's say, time 0.01, COMSOL is going to substitute time here of 0.001 to compute our force, right? This is very important. We give some flexibility to our COMSOL simulations. And we click on here and we click on compute. Okay, this will be a relatively quick simulation. I'm using a 16 GB RAM computer, i7 processor. Laptop is old, maybe 3 years old, right? Not too old. Okay, and this is what I'm getting. If I click on 1D plot graph, here is my graph. Here is my graph. If you want to get another graph, another point graph, you can click again, and if you want to select some other point, you can do it very easily. Here is another point. There is also an option to basically define a function, right? You can define a function and you can plot the input function if you want. Okay, so let us visualize our load here. We can do that, right? We can do that easily. So what do we do? Let me repeat these steps. I'm going to just erase this global, and we erase this. So under the option 1D plot groove graph, we click on global, and here we can basically define a function that we want to plot. In our case, I'm going to basically plot the load divided by a very large number, since the load is in the unit of hundreds and my displacements are in 10 to the minus 6, so I'm dividing by 10 to the minus 7 or 8, right? And I can basically plot. So this is my load. The red line is my load. And you can, of course, you can play with legends. If you click on point graph, you can show legends, and this will be the show legends. You can plot basically, and this line is the input, the red line is the input, and the blue and the green lines are the corresponding outputs of your system. Okay, that would be all for today. Thank you very much for your attention. If you like this video, of course, support our channel or subscribe. Have a nice day.